Hello and welcome everyone to tonight's webinar focusing on parabolas. This session is part of a series schools can use to develop a middle school mathematics elective. The activities in this module relate to parabolas and will be available for download from the Texas Instruments Australia website in the coming weeks. Our previous session, Code by Numbers, is already available from the Texas Instruments website. If you go to the home page, I've made a link there under the activity of the month. So it's right there in the middle. If you click on that, you'll land in this sort of space. Now, you can click on any one of the links to download the complete unit on Code by Numbers, whether you're using Nspire or 84, or if you're programming in Python or BASIC. There's lots of work on coding and pseudocoding, a number. Really powerful stuff in there to help develop students' mathematics in terms of number. Perfect for an entire or part of an elective rather, for middle school maths, which you'll see from tonight that that's the sort of flavor we're delivering. You can, if you want to, just select a single activity. So for example, Euclid's algorithm might sound tricky, but it's not, and it's pretty cool. And it's one of the ones that I know is referenced in VCE mathematics, for example, as an example of coding or pseudocoding. In this session, as the title suggests, we're focusing on parabolas. We won't be spending much time factorizing or expanding. Instead, we're going to take a different approach, which complements the traditional approach, but by providing a context, meaning, and understanding. Just like the Code by Numbers module, it's designed to provide a much richer background for students planning to potentially study further in mathematics at the senior level. The beautiful image that you can see on the screen at the moment, minus all the funny lines and equation, has been generously provided to us by John Sarkinson. John has an Order of Australia, which is pretty impressive for his outstanding contributions to science. He is an operations scientist at Parkes Radio Observatory. And aside from his incredible research and wonderful photography skills, he was also part of the technical support or advisor for the Australian movie classic, The Dish, as you might expect. The radio telescope at Parkes represents perhaps a more common application of parabolas we might see, focusing on radio waves, and we will explore this later in the webinar. But there's some critical features that are often overlooked when we do these sorts of applications. So stay tuned. A less traditional application of a curved surface is a building located at 20 Fenchurch Street, London. The building, that really weird shaped one, is often referred to as the walkie-talkie building. I first learned about this building through a book that I read, a book titled Humble Pie by a wonderful comedian and mathematician, Matt Parker. Now, Matt's book is a must-read for every maths teacher and for any student interested in a career in mathematics related field, as each chapter serves as a reminder to think carefully about mathematics, as the title would suggest. In chapter 1, we hear about losing track of time. On the 14th of September 2014, around 800 aircraft were making long-distance flights above Southern California. A mathematical mistake was about to threaten the lives of tens of thousands of people. Without warning, the LA Air Route Traffic Control Center lost radio voice contact with all the air traffic. Believe it or not, pilots started using mobile phones to communicate. With all the chaos it ensured, it all related to a time bug in some computer software. This and numerous other stories are included just in this first opening chapter. Chapter 2 is where we can use this idea of parabolas. Matt notes that a building doesn't have to fall down to be included under the heading of engineering mistakes. And that's where our building at 20 Fenchurch Street comes into play. It was nearing completion in 2013 when a major design flaw became apparent. It was a lovely sun-filled day, as Matt would describe it, I guess a particularly rare one in London, and the building managed to focus some light on the ground. The focused light was so intense it managed to scorch the doormat at a nearby barber shop, melted the rear vision mirror on a car, and needless to say, the building soon became affectionately known as the Fry Scraper. Apparently it's not the first time, as Matt goes on, that this has happened. The Vidara Hotel in Las Vegas was burning the skin of patrons lounging around the pool area. Chapter 3 is titled Little Data, and Chapter 4 Out of Shape, and you can count on it, and loads more chapters. And just to frustrate you with Matt's sense of humour, the pages are numbered in reverse, which it doesn't sound like much of a big deal but when you're trying to go back to a page, it's actually a little bit annoying. Thanks for that, Matt. So why do I mention that here? Aside from the wonderful example of a curve-shaped building and a inappropriately located focal point, Matt has generously donated an autographed copy of his book as a prize to one of our attendees in today's session. So stay connected, stay tuned, because one of you will be a lucky winner and we will send that book out to you. However, even if you don't win, I can honestly say this is one of the only books I've actually ever read twice. So next time a student asks you, when are we ever going to use this in one of your mathematics class, you'll be able to refer to one of Matt's stories. They are absolutely hilarious in some cases, but as Matt says, it wouldn't be funny if someone died, so all of his comical stories, nobody dies, but there's some near misses. With all that said, let's get started. And we're going to start with a paper folding activity. So if you've got a piece of paper in front of you, an A4 piece of paper, I'm going to get you to put it, we'll call it in landscape mode. The visual gives you some idea of what we're about to do. And then what I want you to do is get your piece of paper and you're going to fold it. Oh, sorry, before you fold it, place a point somewhere around about the middle of the page. So let's say horizontally in the middle, but up from the bottom, I don't know, about 8 or 9 centimeters should do it. So I'll give you a moment to do that. Luckily, I have everyone's microphone switched off so I can't hear all your paper shuffling. Now, once you've done that, what you're going to do is fold the bottom of the page up and create a fold or a crease like you can see on the screen there. So the bottom of your page has to touch that dot. All right? So it's fairly simple. Now, when I did this with some students once, I made the mistake of saying to the students, now do this 20 or 30 times. And I walked around the class and observed one student folding it from exactly the same point, creating exactly the same fold. That's not the intention. The intention here is to do it along different points along the bottom of the page. So you will create 20 or 30 different folds, but all with the rule that the bottom of the page has to touch that point. So whilst you're doing that, let me swap across to my software and let's see if I've got, there we go. Here's a dynamic version of it. So if you're following along and you've done some paper folding, this is kind of what you're getting. Fold over here, a fold there, and a fold there, and a fold there, and a fold there. Now, when I get students to do this, I also encourage them to use their pen to sort of just enhance the fold, that is, to draw a line along it. They may need a ruler depending on how sturdy their fold is and how dexterous they are with that pen. But they create a series of lines on their piece of paper. The more the better. And at the end of it, I get them to stick the piece of paper in their book. Hopefully they have a maths book that they're using. And you get a curve that looks something like that. So let's see how we can create that curve. So coming up now is an opportunity for you to grab your calculator now that you've finished folding. So what we're going to do in the graphs application is reproduce, hopefully, the folds that you will have done on the piece of paper. So that point that I've currently got on the y-axis, it's not imperative that it's on the y-axis. That was the point that we created at the start, and we just place it somewhere on your piece of paper, round about the middle. That line there, commonly referred to as the directrix, is actually the bottom of our piece of paper. So that's how they relate. And that red line, that represents a bisector, or in other words, the crease that we created. It's a perpendicular bisector, and you'll see why that's a perpendicular bisector. When the students do the activity and the paper folding, there's a lot more than what we're covering here. They actually have to measure. They mark the bottom of the page where it hits the focal point and check the line, and they measure the distance, as in on here it would be like from F to P, and then where it crosses the line, and they find out that these two distances from F to the crease and from the crease to P are the same, and when they draw that line, that segment in, they see that it's at right angles, so a perpendicular bisector. So we're teaching a little bit of geometry as we go. So let's swap across to the calculator, and I'm going to create a new document. So here's where you can follow along with your calculator. I'll try and go at a speed where people can follow along. And I mentioned we're going to put a graphs application in. And I'm going to press escape to get the cursor out of the equation line. Now, if you're using the CX2 calculator, there is a nice keyboard shortcut that you can just press P, and that will create a point. So I can go like that, and you'll see they've got the option to do a point. If you're using just the CX, not the CX2, you can still do it. You've just got to go through the menus. So if I go menu, geometry, points and lines, and point, I'm at the same thing. Now I'm going to put my point on the y-axis because I'm going to refer to it later on. If I put it on the hash mark, that is in this case at 0,4, it will kind of be locked onto hash marks, which can be very convenient at times or frustrating at others. That's entirely up to you. It's not imperative. You'll notice that the point tool is still active in the top left corner, so I'll press escape. The next thing I'm going to do, and that's our focal point, or point P or point F, as you've seen on the diagram so far. The next thing I need to create is, if you like, the bottom of the page, or something that we'll become familiar with as the directrix. I want it to be perpendicular to the y-axis. So for that, I'm going to press menu, geometry, and then construction, which is option 4, and perpendicular, not perpendicular bisector, just perpendicular. So option number 1. And it wants, I'm getting a prompt and saying point on. Whereabouts do you want it to be perpendicular to? I want it to be perpendicular to the y-axis. And again, now it's waiting for me to do a second click. It wants to know whereabouts on the y-axis do you want this perpendicular line? I'm just going to drop it again on a hash mark just because I'm going to use that later, but it's not imperative. And our perpendicular tool is still active, so I'll press escape to release it. I would like my perpendicular line to be a bit longer, so I'll just kind of stretch him out a little bit. So just click and drag. If you're using a handheld, a neat trick is put the mouse near the end of the line, then just click in the center of the click pad and hold for a moment until you get that lovely little animated hand that says, I'm actually gripping the line. And then you can just kind of swipe to the left or swipe to the right. That sounds a bit wrong, but never mind. Now, the next step is we've got the bottom of the page and we've got the point that we put on the page. The next step is to create our perpendicular bisector. So again, we're going to use the geometry tool. So menu, option 8, construction, number 4, and this time we use perpendicular bisector, number 3. So It's perpendicular bisector between this point, so I'll click on it, and this line. Make sure it lands on the line. I've actually got the grid happening in the background. Make sure you don't put it on the grid. That's not going to work. It must be on our perpendicular line. That's it. I'll press escape to release that tool. And then again, I'm just going to drag that line out. And what that line represents is the fold or the crease that we create with the piece of paper. So the next step that we're going to do is, well, before I do that actually, I'm just going to drag this along here. So you can see that one advantage of it on the calculator is it's dynamic. But what would be really cool is if we could leave like a trace of all of those lines on the screen. And the answer is we can. There are two ways. One would be literally a trace, but that's not dynamic. The whole idea of this is it's going to be dynamic. So there's this wonderful tool called a locus. So press Menu, Geometry, Construction, which is number 4, and select Locus, which is number 6. And our locus needs a point that's been defined. That's this one here. And I want the locus of this line. And now we have, if you like, a trace, just like the students did with their piece of paper, of all of those lines. And that's roughly what your student's paper should look like, that sort of a curve or envelope. What the students can't do with their piece of paper is this. Now I've pressed escape to release the locus tool, but now I can actually drag this point down and see what's going on. I can see I'm changing the shape of this sort of curved envelope that we've created. I can do the same by grabbing a hold of this line down the bottom. Very similar effect. And the question is this funny U-shaped curve, is it a parabola? You can put your answer in the chat. Is that curve a parabola? And if so, could you prove it? We often get the kids to identify a parabola, and anything with a U-shaped curve, they'll announce, oh, it's a parabola. No, it's not necessarily. Parabolas have properties, and that's what we're going to explore. I haven't seen anyone commit to saying whether it's a parabola or not. And by the way, just throwing an equation in, and I can do that, I can just press tab and go x squared, and of course just drag it and go, oh, it looks like one. But that doesn't prove it at all. It just says it looks like one. There's a lovely Monty Python line, I think it was from Holy Grail. How do you know she's a witch? Well, because she looks like one. Well, that looks like a parabola, but we haven't proven it yet. We get there. So I'll get rid of my equation. Just undo a couple of times. The next thing I want you to do, this time just sit back and watch. So if you're still playing around with the locus, that's fine. I'm actually going to delete mine. Delete locus. So I've still got this crease, but I want to work towards this idea that it's a parabola. Not a formal proof, but a bit of an exploration. So let's try it. I'm going to construct a perpendicular line to our directrix, I'm calling it, passing through that point, and I'll press escape and I'll just run it up to here. This point's fairly critical. You'll see why shortly. The next thing I'm going to do is construct a line segment. So points and lines in a segment that stretches from here to here. This is like when the students do it with their piece of paper. They measure the length of this line. They measure from here to this point here and from here to here, and they find that these two are the same. And that's how this line is actually constructed. It's perpendicular and bisects these 2 points. The next segment I'm going to put in goes from here to here. Now everything's dynamic, so I can still wriggle this thing along. And if you're now wondering, how does this point relate? Well, I'm just going to put the locus back in, the one that we had before. I'm going to put two different types. First one I'm going to put in is the one that we had before, that is moving that one along there and there. And hopefully you can see that wherever that tangent line is, or that, I shouldn't say tangent, I said that out too loud. Let me just change the color of it so it's easier to see. I don't want to change the color of the locus. I missed. Control Z. Where's my line? Line, where are you, line? There it is. Now there it is. Now I'll change the color of the line. Got it that time. And you can see it's kind of, in a senior maths sort of way, looks like it's tangent to the curve at that point. So I'm going to delete this locus. Oops, deleted too much. Control Z. I love Control Z. There we go. And instead, this time, I'm going to construct another locus. Again, this point here, but just this one here. So how is that movement constrained by the one at the bottom? Now this is a geometry object, so I can't just get equation for it. But I could, of course, drop another quadratic function over the top. That would work, but doesn't prove yet that this thing is quadratic. But there's some other nice geometry happening here that we're going to verify. The first thing I'm going to do is draw a triangle. So I go into my Shapes tool. Now, just a reminder that this event is recorded. So if you're wondering, could I do this by myself outside this webinar? Of course you can, because the activity comes with complete instructions, and a recording of this will be up on YouTube very soon. And of course, then you can play it back, slow it down, speed it up, mute me if you like, and just follow along. So there's a triangle, and you hopefully are realizing this other triangle over here looks very similar. So let's check it out. So for that, I'm going to do a transformation. A reflection of what? Not the line segment. You'll notice that the Q there says tab. I'm going to press tab because it's the triangle that I want to reflect. So whenever you have multiple objects in the same space, you can press tab to toggle through them. So I'll click on the triangle, and I don't want to reflect it there. I want to reflect it over here. And now you can hopefully see that it's filling in the other side there. And to demonstrate, I'm just going to color that slightly differently. Fill color. I'll make it yellow. And hopefully you'll realize that these triangles are congruent. So in the midst of a unit on parabolas, we're actually talking about congruent triangles, and the activity series itself asks the students to prove that these two triangles are congruent. Well, if you think about how this segment was defined, or how this line was defined, more importantly, it was a perpendicular bisector. Perpendicular to this line segment on here, and at right angles. So what we do know is that this length, and now I'm going to label them just so I can refer to them here. So that one, oops, try again, label A, point, label it B, and I'll label this one C. So length AB is equal to length BC because that's how we constructed it. We cut it in half. And let's call this point here P. I'm going to call it P, X, comma, Y, because it is on some sort of a curve. It's on this locus thing. So angle ABP is a right angle, so is angle CBP, and line BP or segment BP is common to both triangles, so we've shown that these two triangles are in fact congruent. That tells us that distance AP is equal to distance PC. And if you've ever looked at the definition of a parabola, you'll find it is a set of points equidistant from a fixed point and a line, where the fixed point is not on the line, because let's face it, if you go and drag that, oh, now here's a little tip as well, that says point C. That's because there's a triangle there. I'm going to press tab to access the point underneath. And of course, if we put that on that, there is no curve. So our fixed point cannot be on the line, because it just wouldn't make sense. All right, so could we now show that this thing is quadratic? Well, I'm going to do it just numerically to start with. I'm going to make that 0. Oh, doesn't like it. Oh, that's because that's the point C. Let me just hide point C. That's going to make my life easier. There we go. And this line here, let's get its coordinate. There it is, 0, 4 for that point. So I wonder what this equation is. Well, what we do know is that the distance from P to A is equal to the distance from P to here. Now I can label it again. I'll label this one focus. And just for completeness, I can't help myself. I'll label this one. So how can I express that? Well, this is a vertical distance. So in other words, y minus -4. So I'm going to put a calculator application in here, and we'll do a little bit of maths. Y minus -4 is equal to the distance from P to the focus. So that would be x minus 0 all squared plus y minus 4 all squared, and then square root the lot. So let's do that. Distance, we had an x squared plus y minus 4 all squared. And we get that. It'd be kind of nice if y was a subject. So let's go ahead and do that. And all that. And it suggests that that equation, now you'll see there I could graph it straight away, but I don't want to. So I'm just going to paste it in here because I actually want it in here. And there's our locus. It seems to fit pretty well. We've defined it algebraically. Now, in the actual activity itself, at a higher level, you can have the students define these points. In fact, you can even store them. So if I said I'm going to store that, let's say in YF, the Y coordinate of the focal point, and I'm going to, let's say, store that one as YD for Y directrix, then I could easily change these. So in other words, I could go up here and go, what if I changed them to something different? So in other words, what if I move this one to 3, or -3 rather, and I move this one to 3? Or we could move it somewhere else, like 5. Could I come up with that equation? Well, let's go back in here. This was the distance to YD, and this one was a distance to Y focal point. So now let's try and solve that for Y, and we get this equation here, which let's copy and paste that across. Tab up, paste, and look at that. Again, I mean, you can't even see the locus now. It's sitting underneath there, but we've managed to get it. And now we're heading towards the general equation. And of course, you could store that in XF if you wanted to. And of course, I haven't done oblique directrix because that's just really messy and no one would want to do that in year 9. That would just be horrible for them. So hopefully you can see now already we've got a level of algebra starting to happen. So let's move along. Let's see if we can model that lovely telescope at parks. That's the sort of stuff that we normally do, right? We get some sort of a curve shape and say, oh, it looks like a U-shaped curve. It's a car headlight, it's a reflector telescope, and various other curve shapes that we like to label parabolas. But why are they parabolic? And what properties of our parabola are they actually using? So kids like to model these things. So what I've done here, let's see if I've got it in here. Document, here it is. Now, if you're not sure how to insert this image, you have to do it from the computer software. And you just click up on here and go Insert Image. And then I've selected the image and hit Open, and it's dropped this image in here for me. And thanks to our friend at Parks, we're able to use his image. It is copyrighted to him, so you can't then go and put it in a textbook anywhere, but you can use it with your students quite happily. So, without any other information about quadratics, how to dilate them or anything else, we just get the students to use the software, and we'll go x squared, because we seem to think that these parabolas fall into that sort of pattern. Oops. So once I've got that, I can just grab it and flex it. Perfect. Must be a parabola. It looks like one. Well, kind of. It would be kind of cool if we could locate this thing here. So the idea is that the radio waves hit the telescope, bounce off, and reflect back through here. Well, there's a nice tool on the calculator that says Analyze Graph number 6. And something the kids will soon learn is that this is a conic section, and we want the focus, option 3. We want the focus of this graph. And there it is up there. I'm just going to recolor it so you can see it a bit easier. Let's make it yellow. That's a bit better. And if I just grab this and move it a little bit, you can see, depending on how accurate my modeling is, it seems that the focus hits this little bubble thing. I'm sure that little bubble thing has a specific name, but this is why we use a parabola, or why we have a parabolic reflector. But that's not enough. The kids still don't necessarily understand why all of those amazing properties make this so useful, because just because light rays or radio waves will bounce and reflect through there is not enough. This is where we normally stop with students, and we've missed some of the key information. So what I want to demonstrate here, and this is also included in the files that come with it, is you can get the students to model this situation. So either on the calculator, like you're seeing here, or get the students those to do, get them to stand against the back wall of the classroom. You're going to need to move some furniture, but it's good to get kids up and physically active. You get them to line up against the back wall of the classroom and basically walk away. Oh, sorry, you put a chair or some object, you can stand in the middle. And the idea is that the students walk away from the back wall, but they stop as soon as they get to a point where they are the same distance from the wall as they are from you. In other words, exactly the same as the geometry that we've been playing around with here. So what? Why is that important? Let's have a look. I have one here called the dish. This is another file that gets included with the activity series. So let's have a look at what happens. We think of a wave as coming in as a straight line, and we'll see why the wave might be a straight line in a moment, and we'll just time frame it on. So here's a radio wave that's come in from some distant galaxy, and it's going to hit our telescope and bounce off and go through the focal point. But notice all of those dots hit the focal point at the same time. That's super critical. I'm just sending things back in time. I'm in my DeLorean sending it back. So each of these is a point on a wave that's come from space somewhere. And within the activity series, students have to prove why all of those points go back through at the same time. And it's actually really simple to prove, like really simple. And it's based on the whole concept, the design of the parabola. It relates back to our congruent triangles that we just went through. So our whole wave hits the telescope, bounces back, and all land at the same point at the same time, the focal point. If that didn't happen, we would just get noise at this point. It would be the mixture of all different waves, but it's not. It's the same wave. So also included, and this is a similar version just without the telescope, where you can just model it and watch the waves bounce through. And it doesn't matter what sort of curve you do for your parabolic reflector, bang, they go through. And of course, for car headlights, it's kind of the reverse. The light comes away from the focal point of the filament and heads out into the distance as a nice straight sort of focused light beam, which, by the way, is if you're changing or considered changing your halogen globes across to LED, don't, unless you get exactly the correct LED, because the focal point is slightly different when you're getting LED globes, and therefore you put them in your car headlights. The light source is no longer at the focus, which means now you get a beam that scatters out. That's why it's illegal. Illegal, that is. Now let's have a look. Why do we call it a straight line? When a wave normally comes in, it normally comes in from a point source somewhere. So here's my point source here, and the wave sort of comes out and hits the surface and bounces off. That doesn't look straight at all. But if you move that point source further away, so now it's at, let's say, 288 meters away, so it takes a while to come in. Now it looks almost straight. What if it was further away, like 648 meters? As that wave comes in, you can see here, it's getting pretty straight. So when it's millions and millions of kilometers away, we can call it straight. So all of these files are included with the actual activity, and ones like this, so we can do some of the diagrams and so on. And in this one, we have it scaled. So if you don't want to have to go through the whole insert picture thing, it's included with the activity files. All right, moving right along. Before we get on the ball bounce, there's another thing I wanted to show you. So we've done some modelings of parabolas in terms of perhaps a telescope and light fittings, but there's another thing. We need to get into a little bit of algebra at some point in time. So here's where you can grab your calculator up again. And what I want you to do is, again, just insert a graphs application. So graph, and I'm going to put in f1 of x equals x. Pretty straightforward. And press tab. Tab's a nice shortcut to get back up the top, or control G. And I'm going to put another one in, exactly the same. That might seem a little bit stupid, two graphs of the same thing, but you'll see why. Press tab, and this time I'm going to put f1 of x times f2 of x. Now you could pick it up from the variables. If you're using your computer, it's quicker to type it. Even on a calculator, f1 of x is pretty quick to type. And then press enter. Now what sort of graph will I get? Well, I've got two equations. The first one's x, the second one's x, so it's going to be x squared, right? Pretty simple. Now, if I move my cursor over there, you'll see it's currently pointing at F3. Now, I can't move F3 by dragging it because it's defined by the other two graphs. But again, you see the prompt that says you can press the tab key. So I'll press the tab key, which gets me to graph 2, and then lower down is F1. Now, if you've gone for the origin here, like I have, those crosshairs means that you can translate that graph. So I'm going to translate it across here. I've still got a parabola. Kind of cool. And I'll drag it over here. I still have a parabola. Now I can grab this one as well and drag that. And it's like, okay, there's a few patterns happening here. If you're really adventurous, and students will play around with this for quite a while, you see what sort of shapes are we getting? We're getting some parabolas. And now it becomes a little bit more open, the sorts of things we're getting students to consider and observe. And hopefully most of you have already observed something, and that is that this quadratic, this parabola, seems to be passing through exactly the same point on the x-axis as this line. Or this, well, both lines. And it doesn't matter whether I rotate it, the line that is, it's just doing it all the time. Why? Why does it do that? Well, to help with that, press Ctrl T. That'll produce a table of values. Now, I'm limited to the amount of screen real estate that I have here, so I kind of want to see that table of values with all three graphs displayed at once. So I don't want to make these too small. I don't want to muck around with these settings. There's a lovely keyboard shortcut to ungroup pages. You can press Control followed by 6, and you'll see that page 1.2 has been created. So you can click on it. On the calculator, you can press Control and right arrow. And now I'm just going to scroll down, and you'll see because of my table settings, I'm not going to get to the exact thing that I want, but I'll go back to here. I'm going to double click on that graph, and I'm going to make it something nice and simple like, and these are the instructions that are included in the activity. I'm going to call it x plus 1, and I'm going to call this one x minus 2. And in the activity, students are required to write down the quadratic equation. And it's a nice extension of the code by numbers activity because the students are used to finding the product of two numbers to equal some other number. Hopefully you can see where this might be going. Now when I go back to here, I see that if I multiply this value, that is the result of f1 of x, by f2 of x, 0 times 3 equals 0. So we're getting to the null factor law. And if I scoot up here a bit, we can see it doesn't matter what f1 of x is. The fact is f2 of x equals 0, so the product is going to equal 0. So of course f3 must equal 0. So we're getting to the idea of the null factor law and an explanation as to why this parabolic curve, this quadratic I should call it, has exactly the same x-intercept as our two linear functions. And of course, can we make it go upside down? As some of my students would say, can we make it into a sad face parabola? Of course we can. But here's a parabola that we might not be able to get. This one. Now let me just neaten him up. I'm going to make it that and that. Challenge the students to get this parabola using these two linear factors. And of course they'll realize that you cannot. You might be able to make it look a little bit like a sad face parabola. We move these over here. But we can't get it to land exactly up there. Not the right way up anyway. Let me try something. Let's move this one over here a little. I'll move this one over here a little. I'll move this one over here a little. Oops. To get to the right spot on it. We've almost got it. And of course, if we change the slope here, let's make it say x plus 2. And let's make this one something like negative x plus 2. Oh, I should have moved that up a bit. Oops. Try it again. There we go. We've got a reflection of it, but we cannot get this one. So having done the unit on code by numbers, We could kind of call this one, because we can't express it as a product of two linear functions, it's kind of like a prime version of a quadratic. All of these other ones that cross the x-axis, they have factors. Ones that don't cross the x-axis, as we discovered by null factor law, we'll call them prime. But just like prime numbers, you could kind of come up with an equation for them. So if I drop those down there, if I've got a prime number, I could get two whole numbers, multiply them together and add on, if you like, the remainder part. So our plus c is kind of like the remainder. So we kind of get that this graph here, let's flip that around the other way. It's pretty close. No, it's not. I moved it. Let's just make it negative x. I could kind of get that up pretty close. In other words, instead of just being f3, if I add on some sort of a remainder, look at that. Pretty much nailed it. So these are like my prime quadratics. I can't express them as a product of two linear factors, but I could do the product of two linear factors plus something at the end. And then, of course, we work the students towards what sort of format might they take. And how could you identify them? All right, moving right along. I'm just watching the time. I haven't had too many questions in the chat unless I'm missing them. This one is a nice one, what I've done for years, and it's a really great way. It's very easy to do. I have what's called a CBR2. It's a small motion sensor. Nowadays, you don't even need the CBR2 if you have a TI Innovator and what's called an ultrasonic sensor. You can actually write your program and make your own. And the data drops straight onto the calculator. The advantage of using the CBR2 is it also collects velocity and acceleration information, which makes it good for a pendulum activity later on. Most schools actually have them already. So search around your cupboards at school, you've probably got a CBR2 lying around. And you can either connect it to the teacher computer or you can connect it up to each student's handheld. You'll need a well-inflated basketball. I recommend a basketball over a tennis ball because a tennis ball is too small to focus on and the kids tend to wave the CBR around too much. A good basketball on a hard, flat surface like concrete, preferably not a wooden floor. It absorbs too much of the bounce and you don't get enough bounces. Anyway, what I've done is collected some data and I'll show you how we analyze the data. It's over here. Ironically, it is called ball bounce data. And it looks kind of like this. So this is when I plugged the CBR in and it collected the data. So in other words, the ball was on the ground. It came up, got close to the motion sensor and then went down to the ground and got close to the motion sensor and away it went. So how do I get that to look like an actual ball bounce? So I'm going to insert a spreadsheet and the data has names. So I'm going to link it to, strangely enough, time. And then I'll go over here and I'll link this one to position and then I can graph it. So I'm going to graph a scatter plot and the stuff I want on the scatter plot is that one and position. And there's my upside down ball bounces. It makes sense when you think about the location of the motion sensor. So now I'll go zoom data. How do I fix these? And I'm going to get rid of those dots in the background. That is the grid, because I don't want the grid on for this. How do I flip them up the other way? All right, so let's change that to a function. And I'm thinking it was a roundabout one. No, a bit higher than that. So I'm just going to drag that function up a little bit. There we go. So I'm going to say that that was probably a point of data that was captured when the ball hit the ground at 1.23 meters. So let's go back to here and I'll call this bounce. So what we want to do is 1.23, we're going to tip it upside down. In other words, we're going to subtract the position stuff, run one position, and I'll graph that. So I'll come back here, double click on that, and oops, Change that to bounce. Oops, see if I can type. There we go. And there's our ball bounce data. I can now get rid of that because I don't need it. And drag that up a bit. And now students get to model the parabolas. Now they could, if you wanted to, just do an x squared graph and drag it and put it over there. But given that they know how to actually generate these x-intercepts, let's have a look. I'm going to just do a point. I'm going to do it just somewhere. Oh, that's a bit tight, my x-axis. Let's change that to 1. It's a bit better. Now I'll do my point here, and I'll get its coordinates. Here's where I'm going to need a piece of paper. I think that first ball bounce is about 0.807. Oh, sorry. I moved it. 0.807, I think I said. And now, where would it have hit again? If it came down and landed on the ground, probably about there, 1.63. So, given my linear factor thing that I was doing before, let's change this to a function, and we'll type x minus 0.807 times x minus 1.63, and it's up the wrong way. So let's fix that and put a negative sign at the front. And it needs to kind of get a bit steeper. And if the students have explored enough, they will know that having a 2 at the front makes these things a bit steeper, and making a 3 out the front, I'm going to go to 4.9. That's pretty close. Let's try 4.5. Maybe 4.6. That's pretty good. I've got my first ball bounce. Now I can do my second one, and all on the back of doing some linear factor stuff. I haven't talked about the location of the turning point and turning point form at this stage. All right, where I'm looking at the time, we're getting close to running out of time. Other activities that are included in this, curve stitching. So in other words, what happens, and that one looks a little bit fancy, it's not. It's just a really simple set of lines. So let me just drop in here. I need a one that hasn't got any graph stuff on it. Not that one, not that one. They've all got, let's just do a new one. And again, just a simple graph one. And the students start with a graph that crosses the y-axis at 10 and the x-axis at 1. So let's say 10 minus x. How did we go there? Oh, no, 10 minus x over 10. No, oops. What have I done wrong there? 9. My brain's fried here. The gradient's going to be 10 over 1. That's better. And then my next one would be 9 minus 9x on 2. And the next one would be 8 minus 8x on 3. And the next one would be 7 minus 7x on 3. Just rise over run stuff. And oops, that's 4. And we get this curve. And we can introduce parameters in that as well. And ultimately, we get this lovely big curve through here. Looks like a parabola, doesn't it? Hopefully you've learned already that we can't just say it looks like a parabola. We need a bit more than that. But that, if you want to get really fancy, leads into these lovely things called Bezier curves. So this one has been constructed so that I can watch what happens. So say, for example, A is aiming at landing on B. A is 0.6 of the way along a PQ, and Q is 0.6 of the way, 0.6 of the way along here, and this is 0.6 of the way along here. And if I move them along, it's called a curve of pursuit, but it also makes a parabola. Now, interestingly enough, this is looking really ugly there, isn't it? But if you think of this, the coefficient here is 1, 2, and 1. This XR is just the coordinates of these points, so that's why it looks a little bit ugly. This is like if I said x is equal to 1 minus t and y equals t, this is x squared, 1x squared, plus 2xy plus y squared. And all I've done is put in my x and y coordinates as coefficients in here to get these to fall into the right spot. There's a lot of math sits in behind there because we don't have to get just functions. We get relations as well, depending on where you put those curves. But it's just another lovely application of parabolas called Bezier curves. Now, this whole series that you've been watching along tonight will be available on the Texas Instruments Australia website over the coming weeks. I have a few other commitments, but I should have it up within the next 2 weeks, so you can download all of the activities, either like you saw before as one complete book, or land on each of the individual activities and pick and choose the bits and pieces that you want. And as we're now out of time, it's 8 o'clock local time. I bid you all farewell and thank you all for attending. And have a good evening.